And today it's our pleasure to have Katharine Adamyk from the University of Western Ontario, who will be telling us about classifying stable modules over A1.
Thanks, Martin. Thanks everybody for coming. It's nice to virtually be here. So yeah, I'm going to talk about classifying stable modules over A1. So first, I'm going to start by telling you what those things are. So I'll give a little bit of background on the Steenrod algebra, and then introduce something called the lifting problem. Then the main theorem I'm going to talk about is a classification of Q not local A1 modules. We'll talk about what those are. And then I'll give some applications of this theorem. So we'll start with the Steenrod algebra. Every time I say cohomology, I'm going to mean reduced cohomology with coefficients mod 2. So we know we have a short exact sequence of abelian groups that looks like this, and this gives us a long exact sequence in cohomology. And in particular, we're interested in this Bachstein map from the nth cohomology group to the n+1th cohomology group. If we put these together for all possible inputs x, we get a natural transformation, right, from cohomology to itself, bumping up cohomological degree by 1. It has the especially nice property that it commutes with the suspension isomorphism in cohomology. And in fact, for any non-negative integer, we have the nth Steenrod square, which is a natural transformation from cohomology to itself, bumping up cohomological degree by n, that again respects the suspension isomorphism. It makes this diagram commute. We have other nice properties as well. So you may notice the title of the slide is Stable Cohomology Operations. The Steenrod squares are examples of these. Cohomology operations refers to the fact that we have this natural transformation in cohomology, and stable refers to this interaction with the suspension isomorphism. So this brings us to the Steenrod algebra. This is the algebra of all stable cohomology operations. So that's the first definition. We have a graded F2 algebra of natural transformations commuting with the suspension isomorphism. But we can also view this as the algebra generated by the Steenrod squares, which is what it is. So we have elements square I for all I greater than or equal to 0. And we have these relations called the Adem relations that tell us how to multiply them. In fact, you can generate the Steenrod algebra just taking the Steenrod squares indexed by powers of 2. So those are the ones we'll be concerned with. As an example of why we might care about the Steenrod algebra, the cohomology of any CW complex is a module over the Steenrod algebra. So I work a lot with particular subalgebras of the Steenrod algebra, denoted AN. So this is the subalgebra generated by the Steenrod squares up to 2 to the n. So for example, A0 just has square 1 in it, and square 1 squares to 0. So we get the exterior algebra on square 1. But I spend most of my time working over A1. So this is going to be generated by square 0, which is just 1, square 1, and square 2. And the relevant relations are generated by the ones given here. The really fun thing about working with A1 and modules over A1 is that you can draw them and encode your multiplicative information in the picture. So in all of my pictures, the grading is going to go from the bottom of the page to the top of the page. Each little dot represents a copy of F2. So I'm just saying I've got a copy of F2 in degree 0 on the class 1. Then in degree 1, I've got a copy of F2 on square 1. And then I'm going to denote the action of square 1 by this little vertical line here. In degree 2, I have square 2, and we'll denote the action of square 2 by a curved edge. So not only do I have these squares, but I can multiply them by each other. So let's say I multiply by square 1 on the left. We want to read this like function composition because that's in fact what it is. If we start at the bottom class, square 1, square 2 means do square 2 and then square 1. Whereas if I have square 2, square 1, that would be this class over here on the right. Okay, I can multiply this by square 1 on the left, but the relations in A1 tell me that if I do square 1, square 2, square 1, that's supposed to be the same as doing square 2 and then square 2. So I have this curved edge representing a square 2 action, and I can see if I follow either path up from the bottom, I end up at the same class. So we can see that the relations in our algebra are encoded in this diagram. If I continue to multiply my classes and apply these relations, what I get is something that's 8-dimensional as a vector space over F2, and the highest degree that any element has is 6. So that's A1. There's a forgetful functor from modules over the Steenrod algebra to modules over A1, right? I just forget the action of the higher squares. A natural question we might ask is which A1 modules are in the image of this functor? So equivalently, we might phrase this question as when does an A1 module have a compatible A module structure? Some do and some do not. So I'm going to be focused on this relation at the bottom of the page that appears in the whole Steenrod algebra, but not in A1 because square 4 is not an element of A1. So I'm just going to try to add a square 4 action to each of these A1 modules. So I have A1 itself on the left. And what I'm going to do is add a square 4 action denoted by this bracket from the class in degree 1 to the class in degree 5. So I can see if, for example, I look at the bottom class, if I act on that by square 2, square 1, square 2, I get the class in degree 5. If I act on this by square 4, square 1, I get the class in degree 5. And then square 1, square 4 acts trivially, so that doesn't contribute. So this relation is satisfied by the action of square 4 that I've put on A1 here. This is not the only square 4 action that would have made this relation and all the other relations in the Steenrod algebra work out. And if you need an exercise to keep you busy during the rest of the talk, you can try to figure out what the other ones are. Now that I've put a square 4 action on here, I'm going to let square 8 and 16 and so on act trivially. And this is going to work out for degree reasons because we're only looking up to things in degree 6 here. Okay, so A1 itself does have a compatible A module structure. Now if I look at this module in the middle, square 2, square 1, square 2 acts trivially on everything here, just for degree reasons, right? This element on the left of the equation here is in degree 5. So neither of these classes have something non-zero 5 degrees above them. So the action of this element is trivial. So if I let square 4 act trivially, I can satisfy this relation. And then I'll let square 8 and 16 and so on act trivially as well. So this module can also be given a compatible A module structure. So you might suspect then that the third one is a non-example, and you would be correct. And what happens is I think about the action of square 2, 1, 2 on the bottom class. That hits the top class. So the action of square 1, square 4 plus square 4, square 1 on the bottom class should also hit the top class. But I can't put an action of square 4 on the bottom class because there's nothing for it to hit in degree 4. And I can't have a non-trivial action of square 4, square 1 because there's no class in degree 1 to support that. So this module cannot be lifted to a module over the whole Steenrod algebra. This example is going to come back a lot, so I'll give it a name. We'll call it Upsilon 1. Okay, so that's a problem we're interested in. In order to give the classification theorem, I'm going to say a little bit more about the stable module category. This is the category I'm going to work in. So in general, if I have a ring, the stable module category has the same objects as R modules. And then the morphisms are R module homomorphisms, but we mod out by morphisms that factor through a projective module. And we say two R modules are stably equivalent if they're isomorphic in the stable module category. The category of stable A1 modules has a really, really nice description. So these are two theorems of Margolis. The first one tells us if I have an A1 module, it splits as a sum of a free part and a reduced part. So the free part, as you might suspect, is free over A1, and the reduced part has no free summands. Furthermore, if I have two A1 modules, they're stably equivalent if and only if their reduced parts are isomorphic in A1 mod. This comes from the fact that over A1, being free and being projective are the same thing. So factoring through a projective module is the same thing as factoring out by a free module. So when we, in essence, factor out the projectives in the stable category, we're removing this free summand. One really powerful invariant we have working in the stable category is Margolis homology. So there's a much broader context in which you can define Margolis homology, but I'm just going to focus on these elements Q0 and Q1 in A1. So what are these elements? Well, Q0 is just square 1, and then Q1 is square 2 square 1 plus square 1 square 2. Why are these kind of distinguished elements? Well, they share the important property that they square to 0. And this lets us define homology with relation to multiplication by this class Qi. So if I have an A1 module, I define the Qi Margolis homology of M to be the kernel of this action on the things in degree K mod the image of the action of Qi. Let's look at an example. So here's upsilon 1, one of my favorite examples of an A1 module, and we're going to compute the Margolis homology. So let's start with the Q0 Margolis homology. I'm going to take the kernel of square 1, so that's anything that you don't see a little square 1 action coming up off of. Then we're going to mod out by the image of square 1, so we see the class in degree 2 is hitting the class in degree 3 with a square 1 action. So when we mod out, that won't contribute to the Margolis homology. We'll just get a copy of F2 in degrees 0 and 5. So heuristically, we should think of Margolis homology with respect to Q0 as picking out the dots in our picture that aren't connected to a square 1 action on either side. Okay, the Q1 Margolis homology is a little more complicated, but we can conclude immediately that these top two classes are going to be in the kernel of Q1 for degree reasons. The degree of Q1 is 3, and there's nothing 3 degrees above either of these classes for them to hit. So now if I look at the action of the bottom class, square 1, square 2 hits this class in degree 3, and square 2, square 1 acts trivially. So this is Q1 of the bottom class. And then the opposite thing happens on the class in degree 2. Square 1, square 2 acts trivially, but square 2, square 1 hits this top class. So the whole kernel of Q1 is in the image of Q1, and we get 0 Q1 Margolis homology. An A1 module M is called Qi local if the Qj Margolis homology is 0 for j not equal to I. So for example, our Q1 homology was 0 for upsilon 1. So it's Q not local. You want to think of this as all of the Margolis homology is Q not Margolis homology. So there's a theorem of Bob Bruner that says every bounded below A1 module M sits in a unique triangle in the stable module category between a Q not local module and a Q1 local module. So there are certainly modules that are neither, but if we can say something about the Q0 local and Q1 local modules, this will also give us some information about stable A1 modules in general. So my goals for the rest of the talk are to give a classification of Q0 local A1 modules, now that we know what that is, to use that classification theorem for some computations, and then explore consequences for lifting A1 modules to A modules. Oh, did I see a hand?
Sorry, I just missed, what was the definition of being local again?
Oh, so to be Q not local means the Q1 Margolis homology is 0.
Oh, okay, thank you.
Mm-hmm. Yeah, thanks. Any other questions? Well, I'm at kind of a good pausing point. Yeah, okay. Yeah, thanks again. Okay, so now we want to classify these modules. And I'm going to introduce you to a family that we've taken to calling the Seagull Modules. So upsilon 1 is going to be our one seagull. This is seagull like the bird, not seagull like the person, because it has these little wings. then the 2 Seagull is going to be 2 copies of upsilon 1 linked by the action of square 1. And then the 3 Seagull is 3 copies and so on. If I take the co-limit, this is going to be the infinite Seagull. So when I say the infinite Seagull, I'll mean one that's bounded below, but not above. So let's think about the Margolis homology of these modules. Well, the Q-naught Margolis homology is going to pick out the classes that aren't connected to a square 1. So for each of the finite ones, that's the bottom class and the top class. And then for the infinite one, just the bottom class. And then just as we saw in the example for upsilon 1, the Q1 Margolis homology is going to be 0 in any of these cases. So this is a family of examples of Q-naught local modules. And what I claim in this theorem is that they are essentially the only examples of Q-naught local modules. So take a bounded below finite type Q-naught local A1 module, then it's stably equivalent to a direct sum of suspensions of these Seagull modules, maybe finite, maybe infinite. So just as a reminder, that means as an A1 module, M is isomorphic to this direct sum of suspensions of the Seagulls, plus maybe a free module. I think it's clear, hopefully, what bounded below is. Finite type means that it's finite as an F2 vector space in each degree. It doesn't have to be finite overall. So this is a lot of text, but everything that's on here I'm going to show you again in a picture in the next couple of slides. But I'll give you an overview of where we're going. So I'm going to take such a module, it's bounded below, should say finite type as well, and Q-naught local. And because I'm working in the stable module category, I'll take a representative that has no free summands. So M to the K is going to denote the submodule of M generated by all elements of degree less than or equal to K. And we'll assume M-1 is 0. So we'll induct on K. First, I'll show if we look at the things generated by the classes in degree 0, then we get a sum of 1 Seagulls. Then at each stage, MK mod MK minus 1 will be a sum of 1 Seagulls. And we have to solve an extension problem from the flock of Seagulls we already have to the new Seagulls that we're introducing. So I'll give kind of an example of how some of these arguments work out via this lemma. So the claim is that square 1 acts trivially on any class in degree 0 for such a module. So I'm taking some class in degree 0, let's call it X. And suppose not, suppose square 1 acts non-trivially on it. I'm going to rely very heavily on the fact that Q1 has degree 3. And so the image of Q1 is contained in degrees 3 or higher. I'm using the bounded below assumption here as well. Right? So since my module is Q-naught local, that means the Q1 Margolis homology is 0. Let me go back a bit. So since this class, square 1 of X, can't be in the image of Q1, that means I can't allow it to be in the kernel of Q1, or it would give me a non-trivial Q1 Margolis homology class. Okay, so Q1 has to act non-trivially on this class. The action of square 2, square 1 has to be trivial on this, simply because I know multiplying square 1 by square 1 is always 0. So that's the part in red. So then it must be that square 1, square 2 acts non-trivially. So I'll keep this part in black. But the relations in A1 tell me that square 1, square 2, square 1 is always the same as square 2. That tells me there has to be a non-zero class in degree 2 that's supporting this action of square 2, square 2. So now we look at this class. It also can't be in the image of Q1. So I cannot allow it to be in the kernel of Q1, or it'll give me a Q1 Margolis homology class. So let's look at what the action of Q1 on this is. I didn't draw it in, but the action of square 1, square 2 is going to have to be trivial, because if we follow up the square 2 action on this class, we see it's in the image of square 1. So acting on it by square 1 will be 0. So it must be that I can act on it by square 2, square 1 and get something non-trivial. Okay, this is starting to look an awful lot like A1. And if we look at this class in degree 3, so now maybe this is in the image of Q1. Let's look at the action of Q1 on it. Well, square 2 square 1 on it is going to be 0 because of the relations in A1. Square 2 square 1 on this, if that's non-zero, that would give me a whole copy of A1 in here, but I assumed I had no free summands, right? Over A1, if I have any copy of A1 inside my module, it will split off as a free summand. So I can't allow this to happen. I assumed my module was reduced. So Q1 on this class, there we go. And square 1, square 2 is always 0 for any A1 module. So this class that I've circled has to be in the kernel of Q1. In order not to get a Q1 Margolis homology class, that means it must be in the image of Q1. So I'm assuming there's some class in degree 0 that hits it. Okay, you do a bunch more of this kind of flavor of pushing things around, and what you get in the end is that that class Z that was hitting that class in degree 3, square 1 of it has to be the same as square 1 of X. Square 2 of it is non-zero, but square 1 and square 2 both act non-trivially on this class in degree 2. And this gives us something in the kernel of Q1 that can't possibly be in the image of Q1 for degree reasons. Okay, so after all that, we finally get a contradiction that came from our supposition that square 1 acted non-trivially on X. Okay, yes, so here's our contradiction.
Sorry, Catherine?
Yeah.
You mentioned that a submodule isomorphic to A1 would have to split off. Is A1 self-injective?
Yes.
Oh, okay.
Yeah. Over A1 being injective is also the same as being projective or being free.
Oh, right. Okay. Is it a Frobenius algebra or something like that? Yeah. Okay. Thanks.
Mm-hmm. Thank you. Okay. So we've shown that square 1 on any class in degree 0 is 0. You can use a really similar argument to what we just used to say, okay, now take the class in degree 0 itself. It can't be in the kernel of Q1. Because square 1 is 0, the Q1 action has to look like this little upside down question mark. Look at the class in degree 2. That tells you have to build up a Q1 action on that class. So you see this little seagull shape appear. And of course, there's more work to do in the actual proof of the theorem to show that these all split apart as direct sums. Okay, here's another wall of text that is going to turn into pictures, so don't worry about it too much. So now we're going to take the inductive step. We assume mk-1 is isomorphic to a flock of seagulls. So this is some direct sum of suspensions of the Seagull modules. So I have an extension between mk-1 and m mod mk-1. Both m and mk-1 are q0 local. This gives us that their quotient is q0 local. So we can apply the argument of the base case to show that if I look at m mod mk-1 in degree k, where the first non-zero classes appear, I get a sum of suspensions of 1 seagulls. So this leaves us with an extension problem between mk-1 and the quotient mk mod mk-1. What we're going to do is take a generator x for each new 1 seagull in the quotient. And I know square 1 on that generator is 0 in the quotient. So either it's 0 in mk or it's just contained in mk-1 and it's non-zero. If square 1 of that generator is genuinely 0 in mk, the 1 seagull will split off as its own summand. If square 1 of it is not 0, we'll choose a basis for mk-1 so that square 1 of x is the top class of a single seagull in mk-1. And so I'm just lengthening that seagull by 1. Let me show you what I mean by this. So the key thing is I'm looking at things generated by elements in degree less than k. So on the left here, I have mk-1, right? All the generators here are in degree k-1 or lower. And then I've got these new 1 seagulls from the quotient.
Sorry.
Oh, sorry, was that a question?
No, it was an accident.
Oh, okay, no worries. Okay, So on the left, we have mk minus 1, and on the right, we have the new 1 Seagulls that we're introducing from the quotient, and we're trying to solve an extension problem between the two. So what I show in the long, detail-heavy version of the proof is that either these 1 Seagulls are going to stay off by themselves and become a direct summand of mk, or I can pick the basis for the module on the left so that I'm just attaching this 1 Seagull to the top of an existing Seagull. If m is finite, then we're done, because at some point mk is going to be all of m. If m's just bounded below infinite type, this doesn't quite work, because we can't just keep changing the basis as we go along at every step and assume we can take a nice co-limit there. So what we do is we assume that m has no finite summands. We construct inclusions from mk to mk minus 1 that respect the direct summands, this decomposition into Seagull modules, so that I'm not changing the basis every time. Then I can take the co-limit individually of each summand, which is an infinite Seagull, possibly shifted. Okay, so now we're going to turn our attention to some applications.
Actually, I do have a question now.
Mm-hmm.
So to prove that result about the extension, is this an X1 calculation, or is it a sort of an just work with the actual extension and prove that you can find an appropriate basis argument?
I take the second approach. I think it's entirely possible that there's a more elegant approach via thinking about what X1 should be here. But yeah, what I have at the moment is very hands-on.
Okay.
Okay, so what could we use this theorem for? We're going to look first at some applications to calculations in the atom spectral sequence. And this is actually a pretty classical application of classification theorems for modules over the Steenrod algebra. So just as a reminder, anytime we have a nice space or spectrum, we get a spectral sequence that starts from X over the Steenrod algebra of the cohomology of X and converges to the two completed homotopy groups of X. I'm just going to keep working over the prime 2 all the time. So if I have sub-hop algebras C inside B inside A, I define B mod mod C to be B tensored over C with F2. So I'm thinking of F2 as C module where just everything other than 1 acts trivially. And then this whole tensor product is a B module via action on the left factor. Okay, so for example, upsilon 1, the 1 Seagull, is A1 mod mod A0. And you can think of this as we're quotienting out by the action of A0 on the right, as opposed to on the left. So here, anything that decomposes into something times square 1 on the right is going to be 0. And we see this 1 Seagull appear inside A1. To look at a motivating example, let's consider the spectrum KO. This represents real topological K-theory. So that means, right, if I want to take the real K-theory of X, I can take maps from X into KO. And there's a spectrum little ko called the connective cover that has the same homotopy groups as big Ko in non-negative degrees, but it has 0 homotopy groups in negative degrees. Thanks to Bott periodicity, we know the homotopy groups of little ko are aperiodic. And what they are is Z, F2, F2, 0, Z, 0, 0, 0, and then they repeat. Okay, so what does this look like in the atom spectral sequence? Well, the cohomology of connective real K-theory is known to be A mod mod A1. So the E2 page of the atom spectral sequence is going to look like X over the whole Steenrod algebra for A mod mod A1, F2. There's a change of rings isomorphism that tells you that this is the same as X over A1 of F2, F2. If you have ever computed a projective or injective resolution over the whole Steenrod algebra, you know how nice this is. Now we can compute those projective or injective resolutions over something that has dimension 8 over F2, as opposed to this huge infinite thing. Even better, the spectral sequence collapses on the second page, And we can read off the two completed homotopy groups of little ko just by computing x over this little subalgebra A1. It looks like this. I haven't drawn all the structure lines that you might be used to seeing if you've seen this picture before, but I've drawn the ones I personally care about. So again, each dot is a copy of F2. I'm using the Adams grading here. So the reason for that is that we're converging to the T minus S homotopy groups. So having my x-axis here be T minus S means that each homotopy group aligns itself in its own column. So if I look in the first column, this is telling me that the first homotopy group of little ko completed at 2 is F2. And then if I look in column 2, that's telling me the same thing. Column 3 is empty. So this is telling me the 2 completed third homotopy group of little ko is trivial. So now let's look at the towers. So the X page here is not exactly giving me the homotopy group, right? It's giving me something called the associated graded. So I have to think about how all these little F2s sit together in some extensions. So I've got Z mod 2 in degree 0 here and another Z mod 2. And what that tells me, right, is that I've got something that when I quotient by the subgroup Z mod 2, I get Z mod 2. The little structure line here is multiplication by the class H naught, which in homotopy detects multiplication by 2. So this is telling me that these two Z mod 2s sit together as a Z mod 4. If I look all the way up the column, what that's telling me is that I have a copy of the 2 adducts, which is precisely Z completed at 2. So we can see exactly what we would expect from knowing the homotopy groups of little ko on this X chart. One thing we might want to know is where this H naught periodicity appears. For one thing, it's just interesting to see where do these towers appear, but also it can be easier to study the E2 page of the atom spectral sequence by isolating one type of periodicity at a time. So we're going to isolate the H naught periodicity by inverting the class H naught. This means each H naught tower turns into a tower that's infinite in both directions, and anything that's H naught torsion just goes away. So anytime you see this notation, H naught inverted X over A1, you should think we're looking for towers. How are we going to find those towers? It turns out you can actually find where they are using Margolis homology. So there's a theorem of atoms that says if you take a bounded below A1 module that's free over A naught, then you get some vanishing line on X over A1 of this module. It follows that if I have a bounded below Q1 local A1 module M, H naught inverted X over A1 of M is 0. Why is that? Well, being Q1 local, it turns out is the same as being free over A naught. So we get this vanishing line. Any H naught tower would eventually peak up over that vanishing line because it has a slope that makes it less than vertical in the Adams grading. Okay, so again, Q1 local means the Q naught Margolis homology is 0. So this is kind of the opposite of the class of modules we've been talking about. There's a theorem of Davis that says if you take a module M, which is a module not over A1, but over the whole Steenrod algebra, the H naught towers in X over A of MF2 are in one-to-one correspondence for a basis for the Q naught Margolis homology of M. So if M is an A module, we can use the change of rings isomorphism to say H naught inverted X over A1 of M is isomorphic to the Q naught Margolis homology of M, tensored with the polynomial algebra on H naught and H naught inverse. So that's giving us the H naught towers for each element of the Margolis homology. And then also this class alpha, and the degree of alpha is 4, 3. So that's T minus S degree 4. So what does this look like? Well, here's an A1 module M. You can check, or you can just believe me that this is a module over the whole Steenrod algebra. I can give it a compatible square 4 action and so on. The Q naught Margolis homology is going to pick out these classes X and Y. So H naught inverted X over A1 of this module is going to have an H naught tower for the class X, an H naught tower for the class Y, and then multiplication by the class alpha is going to cause these to repeat every 4 degrees. Okay, but this theorem assumed that we had a module over the entire Steenrod algebra. If we just have an A1 module, this can fail. So if I take my one Seagull, what this theorem would predict for the H naught inverted X term of this module is that I would have a tower in degree 0 and a tower in degree 5, and they would repeat every 4 degrees. This is not what happens. We have just one tower in degree 0. You can compute this pretty quickly using a change of rings isomorphism. Again, it's very useful. So,
Sorry,
oh
Catherine.
yeah.
Can you say a bit more about this class alpha in by degree 4-3? I'm not sure I see where it's coming from. So if you go back to the statement where alpha appeared, yeah, that class alpha.
Okay, so if we're taking, oh, what am I trying to say? Okay, so the way you get this is you take, kind of the change of rings isomorphism, change of rings isomorphism backwards. So now I'm looking at X over the whole Steenrod algebra of A mod A1 tensor with M. So this class alpha is coming from the Q-naught Margolis homology of A mod A1. But alpha is also this class that I should have made a bigger deal about in X over A1 of F2, F2, right? So if I have X over A1 of M F2, then that's a module over this term. And so we get multiplication by this class alpha.
Thank you.
Yeah, thank you. Okay, so what actually led me to thinking about this classification was trying to describe H naught inverted X over A1 in terms of Q-naught Margolis homology for A1 modules that are not necessarily modules over the whole Steenrod algebra, trying to give a generalization of this theorem. So this proposition came out of conversation with Nicola Rica, and what he suggested was that you take a spectral sequence where the first page is what the theorem would predict for your A1 module if it were to be a module over the whole Steenrod algebra, and it converges to the thing you actually want, which is H naught inverted X of your module. I'm using A here instead of alpha, and I'm not claiming a multiplicative polynomial structure here because it didn't quite get there in the result. But additively, this is the same thing as what our theorem predicted.
Excuse me.
Mm-hmm.
So is that the exceptional group E1?
Oh, so this is the first page of the spectral sequence.
Of E1?
Yeah.
Okay, thank you.
Yeah. Okay. What have I said? Oh, and you'll also notice I'm taking here, instead of the Margolis homology of M, I'm taking the Margolis homology of M dual. So I'm thinking of that as just the dual over F2. This is also an A1 module. It has an A1 action via precomposition. The Q-naught Margolis homology of M and M dual is actually the same, but the proof is nicer to see if we think about this in terms of the dual. So this is going to come back to that great theorem from Bob Brunner that says our module sits between a Q-naught local and a Q1 local module. LIM, this QI local module here, is called the QI localization of M, and it has the same QI Margolis homology as M. Bob also shows that the Q-naught Margolis homology of M is the same as what I call the infinite Seagull tensored with M. He doesn't use quite the same notation, but we're talking about the same module. Okay, so I'm going to construct the spectral sequence by taking a filtration on the Q-naught localization of M. We already have a really nice filtration of the infinite Seagull given by the finite ones. So I have a filtration of the Q-naught localization of M that's just given by tensoring each Seagull with M. And the successive quotients are going to look like some suspension of the one Seagull tensor M, because that's the difference between the n Seagull and the n+1 Seagull. I've just added a new one Seagull. This filtration gives me the spectral sequence described here. And you might notice it doesn't really look like the spectral sequence I promised you. So there's some work to do to identify this as the spectral sequence that we want. So let's start with the E1 page. So my E1 page is given to me by x over A1 of some suspension of the one Seagull tensor M, F2. So first, in that first step, I'm just moving the suspension out. So I'm not going to think about the degree. Then I'm using the change of rings isomorphism to say, instead of computing x over A1 of A1 mod mod A0 tensor M, I can compute x over A naught of M F2. So, and then instead of writing the suspension, I'm just writing this as x over A naught MF2 on A to the n, where the degree of A to the n is 4n. Okay, so that's the first step in identifying the E1 page. And now we want to compute x over A naught. This is pretty easy. You can construct an injective resolution of F2 over A naught just by this picture. So nothing super complicated happens in this injective resolution. So we know x over A naught of M is supposed to be the kernel of composing with our structure maps here, Fs plus 1, mod the image of Fs. But let's say I have some map in this kernel. So I've got an A0 map, M, into JS. And when I compose with Fs plus 1, I get 0. Well, that means the image of G is contained in the top degree of JS. You can see in our picture here. So that map has to factor through F2. So I had this A naught map into JS. Now I'm going to get an F2 map out of that into F2. This is an A naught map. So square 1 on this is going to be 0 for all x and m, because I'm factoring through F2 where the square 1 action is trivial. So I've taken some map in the kernel that's going to give me my x group over A naught, and I've identified it with a map in M dual, and that map is in the kernel of the square 1 action on M dual. So you can continue to push this identification through, and this gives you an isomorphism between the x group over A naught of M and the Q naught Margolis homology of M dual. Okay, so this identifies the E1 page. I've got the Q naught Margolis homology of M dual. I've got an H naught tower on that, and then that repeats every 4 degrees via this class A. As an F2 vector space, this is isomorphic to this tensor product with the polynomial algebra we wanted. I just wasn't able to get the multiplicative structure of A. So now we're going to come back to Adam's vanishing theorem that told us if I have a Q1 local module, H naught inverted x of that is going to be 0. Since I know M sits in this triangle between L naught M and L1 M, and H naught inverted x of L1M is 0, I get an isomorphism between H naught inverted x over A1 of M and its Q naught localization. So that identifies what our spectral sequence is converging to. And so we can see this spectral sequence that comes from filtering the infinite Seagull tensored with our module is the same as the spectral sequence that Nicolas proposed, where you take the thing Davis's theorem would predict, and it converges to the thing you actually want. Okay, how am I doing on time? Yeah, I can say a little bit about the differentials. So let's say I have a bounded below A1 module of finite type, not necessarily Q naught local. I can apply the spectral sequence to any A1 module. The D1 differential looks like this. So this is a lot of text. Let me parse it briefly. So I'm taking D1 of some class in the Margolis homology of M dual. That's the B dual there. And then I've got multiplication by my classes H naught and A. So H naught and A, I'm just going to get another copy of each of those. So I'm moving up one in the filtration degree, and I'm moving up 1 in the degree S. Then the class B dual, I'm going to map to square 2, square 1, square 2 acting on B dual. So remember that action is given by precomposition. Okay, what does this actually mean? Well, if I take the D1 differential on the classes X dual and Y dual, square 2, square 1, square 2 on X dual is precomposition of X dual with square 2, square 1, square 2, right? Nothing in the image of square 2, square 1, square 2 is going to be picked up by X dual, right? Because it's at the bottom of a module. There's nothing there that's in the image of square 2, square 1, square 2. But if I precompose by square 2, square 1, square 2, Y dual is going to pick up exactly X, right? Because Y is square 2, 1, 2 of X. So this D1 differential is picking out classes in the Margolis homology that are connected by a 1 Seagull. That's what all that notation means. So here's my spectral sequence for the 1 Seagull. So again, this E1 page looks like a tower for X dual and Y dual. Those are the towers that are the red circles that you see in degree 0 and 5. And then as we increase the filtration degree, those repeat every 4 degrees. So that gives us first the orange squares and then the green triangles. What does D1 do? Well, it gives us a differential between Y dual and X dual times H naught A. So that gives differentials between all these pairs of towers that we didn't want in our answer. So when I take the homology, those pairs of towers go away. There's no room for any more differentials. The spectral sequence collapses. And we get that this is H naught inverted X over A1 of our module M here. I have a conjecture for the higher differentials. The difficulty here is if I want to pick out a 2 Seagull, now I'm not just concerned with what's the action of square 2, 1, 2. I somehow need to be able to take the inverse of square 1 and then go up by square 2, 1, 2 again. And making that inverse square 1 well-defined is kind of where the difficulty is for the higher differentials. I'll leave that aside. So what does all this have to do with lifting A1 modules? So we've seen some things about spectral sequence computations for H naught inverted X over A1. We've seen some things about properties of A1 modules, and these things can kind of feed off of each other. So in particular, the classification of Q naught local modules can help us in our spectral sequence computations. And the differentials in the spectral sequence computations can tell us something about the properties of A1 modules. Let me give you an example of what that looks like. So we've said that as F2 vector spaces, my E1 page is the Q naught Margolis homology of M tensor with this polynomial algebra. When M is a module over the whole Steenrod algebra, so it can be lifted, this spectral sequence collapses on the E1 page, because I know from the theorem of Davis that in that case, this E1 page is isomorphic to the thing I'm converging to, H naught inverted X over A1 of M. So if I see any non-zero differential after the E1 page, that tells me I can't lift my module to a module over the whole Steenrod algebra. So from the D1 differential, I get that if my module has a compatible A module structure, then square 2, square 1, square 2 on X dual is going to have to be 0. Otherwise, I have a D1 differential. So my spectral sequence didn't collapse when it was supposed to for a module over the whole Steenrod algebra. So for the N Seagulls themselves, it's not too hard to compute what the differentials are. You just cheat by knowing the answer. And what we're going to have for an N Seagull is a differential dn, and all the other differentials are 0. So let me show you what I mean by I'm cheating here. So here's the answer we're looking for, H naught inverted X over A1 of the 3 Seagull, for example. If I look at the E1 page of my spectral sequence, it looks like this. I've got those 3 towers I want to end up with, and then I've got these extra towers like I had for the 1 Seagull. For degree reasons, the only way I can get rid of these extra towers is by having a D1 differential that looks like this. Okay, And then I'm looking at this tower in degree 13 is infiltration degree 1. This tower in degree 12 is infiltration degree 4. So that's what tells me it's a D3. Okay, once I take the homology, there's no room for any more differentials, and I know my spectral sequence collapses. So a corollary of this is that none of our finite seagulls lift to modules over the whole Steenrod algebra. You can show by hand, in fact, that the 2 to the n Seagull lifts to an an plus 1 module, but not an an plus 2 module. So I'm certainly not claiming this is a proof of a new result, but it's an interesting thing that kind of just falls out of this spectral sequence. This tells us that the Q0 local bounded below A1 modules that can be lifted to modules over the whole Steenrod algebra are going to be stably equivalent to sums of the infinite Seagull or to 0. Because I know it's stably equivalent to a sum of some Seagulls, if any of them are finite, my module couldn't be lifted. Okay, so if I have in general some appropriately finite A1 module, we can hypothetically compute all of the differentials and use those to find obstructions to lifting. But to do so, we would need to decompose the infinite Seagull tensor M into a sum of Seagulls. This is kind of a nightmare to compute. Like, this is a huge tensor product. And then even once you've taken the tensor product, you have to find the decomposition of that into direct summands that look like the Seagulls. But in the case where n is equal to 1, because we have an explicit formula for D1, we don't have to compute this tensor product. So I have this correspondence between a non-zero differential in the spectral sequence. If it's D1, that corresponds to the Q0 localization, the infinite Seagull tensor M, having a direct summand that looks like a 1 Seagull. But because I know what D1 is, I know that corresponds to non-zero classes in the Q0 Margolis homology of M that are connected by the action of square 2, square 1, square 2. So I don't have to compute this nasty tensor product to detect this obstruction to lifting my A1 module to an A module. So moving forward, continuing to think about this stuff, I'd really like to determine the conditions for M that correspond to an N Seagull appearing as a summand of this localization. I'll skip that. So thank you very much. And
All
I'll
right,
take
let's
more
unmute
questions.
ourselves and thank Katharine.
Thank you very much.
Thank you all.
Are there any questions?
Hi, Catherine.
Hi.
Hi, nice to meet you. Thank you for your nice talk. I have a stupid questions. I wonder, like, the Seagull, this is the Seagull infinity, is it able to be realized as a homology of some spaces, or yeah?
Oh, man. I think no,
cofiber-
but I know Bob would know.
The infinite Seagull?
Yeah.
Epsilon
Yeah.
infinity? Yeah, it's the cohomology of the cofiber of the reduced transfer from BC2 to S0 up to suspension. So for BC2, you've got, if you leave off the bottom class there, you're looking at the cohomology of RP infinity.
Mhm.
And now you've got a reduced transfer from BC2 to S0, take the cofiber of that, and that gives you a square 2 on the bottom there. Another way of thinking about it is the Tom complex of -1 times the line bundle over RP infinity. Then you have to knock out the cell right above the bottom. There would be cells in every dimension from the bottom up, but you have to get rid of that one in the right above the bottom. So you take the fiber of that. So that's another way of looking at it. So yes, it can
Thank
be
you.
realized.
Okay, thank you.
Yeah, thank you, Bob.
I have a question as well. You mentioned that if your A1 module lifts to an A module, then the spectral sequence you were describing collapses at E1, right?
Mhm.
And so the differentials can be viewed as some obstructions to liftability. Are they a complete set of obstructions? So if you know that the spectral sequence collapses at E1, does that imply realizability?
Yeah,
Liftability?
I have no particular reason to believe that. Obviously, it would be lovely, but yeah, I have no evidence
Okay.
for that. Yeah, and my gut feeling is maybe no.
Yes, well, I'd just also like to thank you for a very beautiful talk. There's a 1962 paper by CTC Wall where he looks at what is actually Q1, sorry, Q0 local A1 modules. And he proves that they're what he calls near simple. So that if you have one of these M, then there's a free module F mapping onto M, and so that the kernel is the suspension of M. That it sounds a little bit like this must, I mean, it must somehow be similar. I don't know if you're aware of this paper. It's by, but it seems like it's. I mean, it's not a very long paper, and sort of his last example is basically that your 2 Seagull is kind of a counterexample to what, something he might look for. So it's a different. So he doesn't give a classification like you do. There's sort of a Davis and Mahold have some papers where they calculate, which they use to calculate x over a of 2 or reducing x over a of 2 computations to x over a of 1 computations, where they use a spectral sequence that they build by looking at sort of a filtration a bit like the one you have and get exact couples. And they also have trouble getting the multiplicative structure. But there is a different approach to the Davis-Mahold spectral sequence that Bob and I have written about, which gives multiplicative structure. So there, if that's something you're interested in, then maybe that's something to look into.
Okay.
I mean,
Yeah,
it would be
thank
usually for these for actual computations, it's obviously very helpful to have multiplicative structure around if you.
Yeah.
I wanted to ask about the theorem. You mentioned a paper, a theorem by Davis. There's also a paper by Peter May and Jim Milgram on which I think says roughly the same thing. Is there a difference?
Okay.
So they have a. I think they're saying that in the H0 towers, basically they're saying that the differentials in the H0 towers are the Bockstein differentials. Well, so there's a Bockstein spectral sequence from the mod 2 homology to the
integral.
To the integral homology, and I guess so in particular they would say that the H0 towers correspond to the mod 2 homology. I'm sorry, I'm sorry. The E1 term would be the mod 2 homology, but taking the homology with respect to square 1. So the E2 term would be precisely the H0 towers. So the Margolis homology.
Okay.
Well, I guess I should just look at the literature to check. I mean, it may be that they are talking about A modules that are actually the cohomology of some spectrum. Since they're actually talking about the atom spectral sequence of something. So I suspect that they're talking about the topological situation, whereas you have the purely algebraic, or Davis might be talking about the purely algebraic situation. But it's yeah. No, but it looks. I guess there are many situations where higher differentials end up being kind of higher order operations rather than primary operations. So you know, it's fully possible that getting a kind of first order description of the differentials might not be so easy. Anyway, thanks.
Yeah, thank you.
Hi, Catherine, you have a classification of the indecomposables. Do you also know what all the maps are, the morphisms? Like, do you know the category? Do you know the whole category, or just the kind of the objects?
Let me think about that. I think, I haven't thought about this, but let's see. I mean, I think you're, well, okay. So definitely we're only concerned about the maps between the seagulls, right? Because the maps between the free parts are going to be trivial in the stable category. And I think you're going to be pretty limited in the ways that you can map one seagull into the other. Like, I think it's going to have to. Okay, no. I would have to think more about this before giving a coherent answer.
Okay, thanks. Very interesting talk.
Thank you.
If there are no further questions, let's thank Katharine again.
Thank you very much.
Thank you all for attending.